Okay, good morning, everyone. I'm sorry. I hope you hear me now. I had a slight technical issue and I'm still trying to see what has just happened. 1 second. I have to get my screen back here and my apologies. Let me see. I hope you can all hear me. I'm just going to open my live chat here. Can you all hear me? Is it okay? I hope the stream has just started. I'm just going to wait till I see something from you, and then I will. Oh, you can hear me. Thank you. Thank goodness. No echo. Sorry about that. Sometimes strange things happen. YouTube just logged me out. I don't know what happened. So this is what happens when you live stream. You can hear us. Very good. Well, good morning to you and thank you for your patience. We just had a tiny delay. So today it's going to be really exciting. I just have to see how I can at the same time see your comments so I can. No echo. That's very good. No echo. That's good. I was worried about that. Okay, very good. Well, we have something really exciting this morning, but before we do that, I just wanted to jump back. I can't always see your comments. I'm going to jump backwards and forwards because I was logged out of the other computer and I don't want to waste any of your time, so I'm going to get straight to it. Let's see now. So what you see now is the episode from last time. I just wanted to make you aware of two things. The first one is that there can be technical issues, and that's why your comments are very important. And I'm going to jump backwards and forwards to make sure that I see your comments. And the second one is which is really important, is that just underneath from the last episode, please look at the download button. You see the download button, that what I'm showing you there. You can download the images. I've done a very nice color image of NGC 4945 for you, and this episode is going to be all about colors. Okay, so that's good. I'm just going to jump back now. Or let's see. Give me a minute or so to just rearrange the screen so that I can also see your comments somewhere, because this is a little bit of a pity. Just have to see, because I didn't anticipate that. So here we go. This should be fine. This should be fine. Okay, let me just write hello. So there we go. Okay, that's fine. I think we'll cope like that. Okay, so today's episode is rather interesting because we are jumping right back into the Milky Way, and what you can see there is indeed the Milky Way as seen from the southern hemisphere. This is an image that I took when I was in Australia, and it's just a 30-second image, and it gives you a very, very nice overview of the center of our own galaxy. That is right in Sagittarius. So what I'm going to do now is I'm going to zoom in. I'm going to zoom right in. And what you see here is this funny-legged monster there. I mean, these they call this Sagittarius. But you see these two legs. I'm just going to try and get an arrow there so you can see that too. Here we go. There's my arrow. So you can see this is the one leg of Sagittarius that I'm looking at. And then you have the other leg. I don't know if it's a leg, but anyway, I call it a leg. And this is rather interesting because right in between lies a very beautiful object. And that's what we're going to look at. And that is the very, very bright emission nebula called the Lagoon Nebula. And the other one is called the Trifid Nebula. And both are very, very beautiful. And they are both so-called Messier objects, which means they are very visible from the southern hemisphere. 1 second, I'm just going to see if I can bring up your comments again, just make sure everything's still running. So I'm jumping backwards and forwards. Yes, hi, a photo shoot is also there. So I wanted to say hello to everyone. So that's important. And I just want, before I forget it, I do want to say that I had a little bit of homework. before we continue, and there was a question from Mike Chilson. I don't know, Mike, if you're here today. I hope you are. But you had a very interesting question. Last week we did globular clusters, and your question was, do you know if there is a higher incidence of binary systems? Binary systems are stars with a companion star, so they are very common actually. We don't. Our own sun is certainly a monosystem, not a binary system. But he said in a globular cluster, which is basically a thick agglomeration of stars in a spherical shape, so we have hundreds of thousands of stars, and they're very old. Is it very possible that you would have binary stars in such a system? A very good question, very interesting question. I actually went into that, and I found this rather intriguing because the answer is not simple. The answer is not simple because there are very few globular clusters that even with big telescopes you can actually go and look into. Now, what astronomers assumed, and I would have assumed exactly the same, is that binary systems would exist it would be very difficult for binary systems to exist in globular clusters for the simple reason because there are a lot of gravitational forces, and because stars are very close to each other, if there's a supernova or something else going on, you would certainly disrupt the binary system. But as it turns out, in 2014, they looked at M4, which is a large globular cluster very close to us, and they found out that there are about 15% binaries in there. 15%. That came as a big surprise, and it is still unclear why there is such a high number. It's so the answer actually is very. The question is more profound than you could even think because the answer is unclear. We in astronomy always get new perplexing answers. The deeper we dig, every time we think we understand something, there are more perplexing answers and more questions. So the answer is binary systems are not well understood in globular clusters. Okay, isn't that interesting? So come up with your brilliant questions. Just throw them at me. This is really interesting. Wow. Yes, Brian. Really wow. So that was a great comment. Okay, so let's go on then and let's dive right into Sagittarius. That is today's episode. So I will just be a little bit patient with me. You can write your questions down. I will jump back every 5 to 10 minutes back to the screen because I can't see it because, as I said, my other laptop has logged me out. So I usually look at the comments there. So I'm jumping back from one screen to the other. So I will... if I miss any comments, just write them and I will jump back every 5 minutes. But this episode here is incredibly intriguing because we are going to look at these two objects. But before we do that, these two emission nebula, I just wanted to point out that this star where the arrow is pointing at the moment is called number 2 Sagittarius. 2 Sagittarius. And that is very, very close to the galactic center. Very close to the galactic center. That means that is where there is a black hole. Now, if you think that the black hole is very close, there's nothing to worry about. The Earth is not going to be swallowed up by any black hole in any near future, okay? There's nothing to worry about. How are globular clusters formed, Brian asks. Yes, well, that is this is another... Brian, that's another quite a difficult question, and I think I will leave that answer for next time because globular clusters are very, very ancient structures. They're much, much older than our own Milky Way, and it is not. I think it is worthy of a longer answer than just giving you a short answer. Jacques, yes. Very nice. So it's a great question, but it's a question that I would like to dig into deeper. Okay, so, but anyway, we are looking here where the arrow is at the moment. You're looking right into our own, into the center of our own Milky Way. They call this the galactic center, and that's where everything's rotating around. It takes our own sun hundreds of thousands of years to rotate around the galaxy, actually. So it's a long, long path, and it's the whole solar system. So we just ride along around around the galactic center. Now you would say, oh my goodness, there's a black hole. Isn't that very dangerous? I've seen all these movies and so on. Well, it's not like that, really. It's not. Because we have a very quiet black hole. And also, black holes, even of the large size that we have in our own Milky Way are only dangerous, and I say that in inverted commas, in about a range of 10 light years. 10 light years. So light traveling 10 years to the black hole. That is what we call the immediate vicinity. We are 27,000 light years away, something like that at least, plus minus a few years, of course. That's very difficult to discuss, but it's very interesting because the own black hole is under very top research. It's very current research, and they're actually looking at the so-called spaghettification. Very interesting word. Spaghettification is the elongation of objects as they get closer to a black hole, because the gravitational constant varies a lot as you come. So nothing to worry about, but that's what we're pointing at. And if you ever come to the southern hemisphere, that's what it looks like. Can we see it here in the UK? That's a great question. The answer is probably yes, because, and I'll tell you why. The objects that we're looking here, that is M8 and M20, are designated as Messier objects, and Messier objects were first observed by a French comet hunter called Messier in 1780 something, if I remember correctly. From Paris. At that time, Paris was very dark, and Paris is at the 49th latitude, the same as Stuttgart in Germany. Now, the UK is typically above 50 degrees, so I think London, if I remember correctly, is at 51. And of course, if you go more and more north, to Scotland, of course, it gets more and more difficult, right? But if M8 and M20 can be observed from the UK, so you would probably see it fairly low in the horizon, okay? So it's of course much easier when you're in the southern hemisphere, okay? M20 is very difficult to see under heavy light pollution, and that's absolutely correct. That is the problem. I mean, you've got these beautiful bright objects, but I think, in the UK, if you go to Cornwall. I think Cornwall has quite clear skies. They've seen some. I think the solar eclipse a few years ago was seen very well from Cornwall, as far as I remember. So, but you're absolutely right. That, by the way, you talk about heavy light pollution all over Europe. Except for some more remote areas. Okay, you're absolutely right. I mean, that includes Germany, that includes France, it includes most of Italy, at least northern Italy. The Netherlands, the UK for sure. The UK also has high humidity, which makes it very difficult. That is absolutely true. So you have to go to drier areas to see that. By the way, there was an interesting episode on the BBC, which you may have seen. They were talking exactly about light pollution with Brian Cox. There was just a few days ago. High water, Miss High. So what was interesting about that, before I jump into our topic today, as I'm just deviating a little bit, was because they were using Siding Spring 2, and there was a girls' high school from Yorkshire, and they were using the telescopes, in fact, and they were doing some color images, and this was incredible that they were doing this just a few days ago, and this was showing live on the BBC. For those of you who live in England, the UK, you may have seen that. You may have seen the brilliant episode that Brian Cox gives. I mean, really a gifted next type of David Attenborough. Beautifully done. Okay, well, let's jump in again. So I'll look at your comments in about 5 to 10 minutes. So just keep on writing them. I will not look at them because I have to concentrate on the episode now. So as we jump in further and further, we're having a look here now. There indeed is the Lagoon and the Trifid Nebula. Okay, these beautiful, and the first thing that you notice is it's surrounded by millions of stars in our own. This is all from our own galaxy. These are stars from our own Milky Way. And what is so fascinating is the Lagoon Nebula on the left looks incredibly bright, and it's really a star-forming nursery. And it has this reddish color, and we'll get to the reddish color in a moment. And then you see a little bit smaller to the right, you see the Trifid Nebula. Trifid comes from the word 3, so divided by 3, and you can see a sort of reddish and bluish. So let's zoom in a little bit further again. And this is actually an annotated image, which I automatically annotated. So it gives you well-known stars and so on. And you can see beautifully now the Trifid Nebula consists of a red and blue nebula, and we'll get to explain what that is. But let's jump to the telescopes now, because that's why we're here. So I'm just going to see where my telescope page is. 1 second, and then I will switch over. Let me just make sure you're all still there. 1 second. Okay, now I can see your comments in. You say can be seen well from badly light polluted Sydney, Australia. That's interesting. Well, I'm going to Sydney on the 17th. I'm arriving there on the 19th of April. I'm going to have a good look. Pamina's also there. Hi, Pamina. Very nice. Okay, so let's have a look. Let's have a look now. You can see those are the telescopes live. So it is just in Australia after it's 2:17 a.m. there. It's very, very early. And we're going to jump straight to our telescope here. And let's do some imaging. So I've done this already, and I just wanted to show you the result, and then we will get straight to do color images. So here we go. That is the Trifid Nebula, and it's not in color. And I think some of you may have been disappointed. You looked at some emission nebula and say, well, that's very nice, but why are they not in color? Well, this is just one single. This is the so-called luminance of that of the image, and I'm going to show you now some images that I took earlier, earlier, the red, green, blue, and also the luminance, and I'll explain to you how to make a color image, which is really exciting, and then we'll get into the details of the nebula. So without further ado, I'm going to jump now onto showing you how we compose color images. So let's see. You should be able to see the window. There are several tips. So I can see your comments also now. I've got it on the other screen. So there are several different softwares for composing colors. It's not very complicated. So what you do is, with a telescope, you take a luminance, a red, green, and blue. And I've just taken 4 images. And what we're going to do is make a quick color composition. I'm using CCD Stack here, but there are other programs that are very well known. Another one is Maxim DL. There are so many good programs, but I'm going to use this one because it is very intuitive. So let's get right into it. And I'm going to do the Lagoon. No, let's do the Trifid Nebula. Where are we? Let's do the Trifid. There we go. Let's do the Trifid. That's the one. So I'm going to open four images here. I'm going to import them now, so just hang on. This is all live. There we go. And this is really beautiful. So I'm going to jump from image to image. Now, what you cannot probably see on the top of the screen, this is the luminance. Okay, the luminance is the sum of all colors. So it is going right from blue to, it's like a black and white image, basically. A black and white image and has no spectral preference for any color. Okay, so it takes red, green, blue at the same time. So that is the most detailed image of the Trifid image. You can see it really, really looks beautiful. It's a 5-image image. And then we jump over, and this is the red. So you can see that's going to be the red color, and then we jump to the next one. And you see how different it already looks. Look at the green. You can see a lot more of the lower nebula, and it's always good to look at the different color. And then you see the blue looks different again. So you can already see that the color image is going to look quite fascinating. So what I'm going to do now is I'm going to compose a color image. But in order to do that, I have to do something which we call aligning. Now, why do we align images? If I just make a color image of these, it's going to look like an image out of focus, because all the stars have to be aligned. They have to be exactly on position, because they never are exactly on position. The scale changes and many others. There's small rotation in telescope, there's atmospheric effects, and so on and so on. So at first, I'm going to open the top window and I'm going to use what we call register. Now register, now this looks like something really strange. What it's doing now, it's trying to find the so I've got it. 1 second. I just have to bring this over to the other screen. There we go. Now you can see it. it's called registration. So registration is looking at the stars and trying to align them. So I'm going to say align all now. So now it's going to think a little bit. It's going to think, whoops, how am I going to do that? And there we go. And it tells me the error is 0.012. So it means good aligning is possible. So I'm just going to say apply. And what it does now, it's found certain stars. Let me see how many those were. It matched 22 stars. And now it's going to use some interpolation to align all stars. So I'm going to say apply to all. Okay. So now it's going to do some maths and going to align them all. So it's going to take a minute or so. There we go. I've got a fast computer. So there we go. Now they're aligned. And now, if I go through them, I'm blinking now, you can see they're all aligned, right? They look different, but as you can see, they're perfectly aligned. The stars match and everything. So looks good. So now we can make a color image. And that's what we're going to do. Create. Oops, and it's again on my other screen. So let me just pull this over to this screen so you can see this. There we go. So you can see it automatically recognized the luminance, the green and the blue. Now the red it didn't recognize, and the reason why it didn't recognize the red is because the telescope designated with R instead of red. But that's no problem. I just did it and then I say create. So now it's creating an image, and then you first look at the image and you think, oh my goodness, it looks ugly. What's gone wrong? Well, the software doesn't know how to weight the thing, so we have to tell it now, and it's already hinting us. Tell me where the background of the image is. What color is the background? So I'm going to choose with my mouse an area somewhere on the side, on the screen, and I'm going to say, okay, this is it. I'm just going to pull this other window over too, so you can see all the windows. 1 second. See if I can get that over. No, that's not. Okay, never mind. And I say OK, and then apply background. Yes, and that looks a lot better, doesn't it? And already you can see how quickly we did that. In no time we did, and that's actually what these what the schoolgirls also did. They composed a color image, and it's quite impressive how out of these out of the red, green and blue, and just single images, you can already see the colors. Now, usually you would see the bottom image, the bottom nebula a little bit more blue. So what we can do now, and let's hope I can get this over. This is difficult on my screen. Yes, I can. Here we go. That's what I wanted to show you. Another window opens. What aperture telescopes? I'm going to answer that question. It's a great question. And Peter, I will answer that question in a second, because I'm going to get right to the telescopes, because you have already guessed what I'm going to get into. It's quite important, especially for the Lagoon Nebula. So this was taken with, we'll get it with, let me just finish this part, and then I'll tell you what aperture this was. Okay, so we can give it a little bit more blue, which I will do at the moment. By the way, one can adjust these colors, and already you can see the reflection nebula here is coming out in much more blue, but you can adjust the colors, okay? You can adjust the red, the blue, and so on. I won't do that very much now, but you can see how quickly we got a color image. And you can also imagine that if we took several reds, green, and blues, you would get a beautiful in-depth color. Now, there are some streaks on here, which, by the way, you can get rid of. This is no problem. These are very typical. They're called blooms, and we'll deal with that with the Lagoon Nebula, okay? But coming now to Peter's question, let's see where this was taken. Let me get back to my files. 1 second. Where are my files? Let me just find them 1 second. Let's see where the Trifid. Okay, I'm going to bring the window back in. There you go. So this was taken with T27. Now T27 is a marvelous telescope. So this is a 0.7 meter aperture, 0.7 meters. That is huge, Peter. Okay. So those are the ones that I just showed you. So within 5 minutes of exposure, we got an incredible depth here. So I hope that was that was fairly simple to see what we've done here. So I'm just going to put the comments over here so I can see your comments. And I'm going to jump back to the other screen now. And I'm going to show you what the image really can look like. I mean, this is incredible. So if you really, really go deep like our friend Joseph does, this is the type of stunning details you get. And these stunning details are exactly the type of details that help us understand what this beautiful object is really about. So he's taken several hours of depth here, and he's also done what you call narrow bands. So narrow bands is taking the oxygen, the hydrogen alpha, which causes these red lines, and also the sulfur, and you get this beautiful composition here. Isn't that marvelous? I'm just going to zoom in even further, and as you can see, the image here is annotated. Okay, so what are we looking at, and why is it so red and why is it so blue? Well, typically, and you may remember this from the Running Chicken Nebula, it was my first episode, emission lines are caused by hydrogen. Hydrogen is about 75% of the molar mass of the universe is filled with hydrogen. The rest is mainly helium, and then you have all the other elements which make a tiny percent of the of the what we call the baryonic matter of the universe. That's not taking dark matter, of course, and dark energy into consideration. So that's about 4.9% of the universe. Okay, and that is mainly the abundance of hydrogen. And now what's interesting about hydrogen, it ionizes very, very simply. So what happens is you have these strong ultraviolet rays coming in from young stars. We call them O stars. And there where this, let me get my arrow there, right here, where the designation here, where there's an annotation for a star, that is where a very, very young bright star is positioned right in the nebula, and that is giving this giving a lot of ultraviolet light as ionizing neutral hydrogen. So it's being ionized, it's stripped of its electron, and then after a while, the electron finds a lonely proton, recombines, captures an electron again, and then the electron emits a line as it cascades down from it's, in this case, it's the Balmer sea. It's called from N3 to N2. Don't worry about all the details, and it emits this beautiful hydrogen line, and that's why you see this beautiful red. And now what you also see, which is quite, so this is all caused by very, very young stars, very, very typical. All these are young stars that you see here, okay? All these are young stars, these arrows, all very young stars. Now what is funny is, where does the blue color come from? Blue is very, very unusual, actually, in the universe as a color, because all the other colors that we know, the oxygen, the sulfur, and all that, are usually reddish or yellowish or so on. They are not really blue. So this is where it gets really interesting. So I'm just going to move over now. And what's interesting is this whole nebula, let's take the wide view again. This whole nebula is embedded with this sort of blue, which looks looks a very, very fine blue dust. And it's called a reflection nebula. It's the same reason why the sky is blue. The sky is blue because they're tiny aerosols. They're tiny aerosols of mainly nitrogen in our air, and they cause a scattering of sunlight. And they have a preference for shorter wavelengths, which is for blue. And that is why during the day, our sky is blue, and in the evening it's red, because the long red rays pass right through the atmosphere and they don't get scattered so much. And that's so what you see there is scattered light. And in actual fact, it is very possible that the reflection nebula, the blue reflection nebula, which is just a reflection of from the starlight, is not associated in any way with the emission nebula of the Lagoon Nebula. So they are, of the Trifid Nebula. So they're not associated with each other. And this object is about 5,000 light years away. I forgot to say that. This is about 5,000 light years, okay? So really, really beautiful, intriguing object. And as you can see, as when you really go into make a beautiful color image over many hours, this is what you can expect. Okay, there's one more thing to say about the Trifid Nebula. This is something really beautiful from the Hubble telescope. And you may have seen the pillars of creation. The pillars of creation in the Eagle Nebula. This looks very, very similar, doesn't it? And that's exactly what it is. These very, very thick dust, this very, very thick dust, they have certain pillars coming out, which you can see there. And this is a marvelous picture, really. And these are indeed pillars of creation for new stars. There's a very bright star behind that is causing a lot of ionization and so on, and a lot of turbulence in the dust. And that is these very, very thick dust centers and these pillars are believed to be the new centers where stars are born. Very good. Okay, now that brings us then to the next and the final image. That's the Lagoon Nebula. Okay, so we're going to jump now to this very, very bright Lagoon Nebula. And to Peter's earlier question, let's see where it was. Yeah, let me just jump down and look at your comments. That's beautiful, isn't it, Pamina? Yeah, it is. It is 5 minutes. Yes, it is 5 minutes. It's right. That's 5 minutes each. And it's done basically, Peter, because we have very, very large telescopes. We have an aperture of 0.7 and 0.5. So let's jump to the Lagoon Nebula and let's do a composite of the Lagoon Nebula image, which I also did earlier today, just to save time, so we don't have to do it live with a telescope, because I want to show you again how to do this. And now it's going to be very interesting, because we're going to compare two telescopes with each other, because you were asking how do the apertures work and what is actually the difference, and this is where it gets really interesting. So I'm just going to put the, oops, I have to just, now what did I do again? There are your comments, sorry. I have to just move this back over again to my other screen so I can always see your, and then I'll jump. There we go. It's fascinating, isn't it? There we go. Okay. So let me just jump back. Jump back to my screen here. There we go. And get rid of the arrow. Yes, and now we will do the Lagoon Nebula. And the Lagoon Nebula is taken with two different, this is really fascinating. I'm going to import a lot of images now. And I've taken two different telescopes to really show you. So let's just, hang on, I need to get back to this. I'm going to close this now. I'm going to say File, remove this image, and I'm going to open the Lagoon Nebula now. Let's do that. And I've taken two different telescopes here, so we're really going to do some incredible work now. Open them all, and we're going to have a look at these pictures, and then we're going to comment on them. 1 second, I'm just going to make sure I find your comments still. There we go, I have them. Okay, now this is rather interesting, what we see here. What we see here looks, first of all, it's, 1 second, I just have to find my mouse. Here we go. I'm going to jump through the images quickly. So this was taken with T27. Okay, that's T27. That's a 0.7 meter aperture, and that is the red, and this is the green. You can see how intense the red is. So we can expect, look at that. Look at the beautiful red. You can expect a lot of red in this image. Look at the green, and that is the, that's the green, that's the blue. And then you see the other ones. And you can notice this was taken with T30. That's a 0.5 meter aperture. And you can see these long streaks, and you think, oh my goodness, my image went wrong. What has happened here? Well, this is very, very normal. This is nothing to worry about. If you look at the Hubble images, they have these type of things. It's something that fortunately software can deal with. And these are called blooms. Okay, let me just explain to you what a bloom is. Here, you see these long, let me just get my arrow back. You can see these long streaks here. These are called blooms. And what a bloom basically is, it is when you have an image that is that is oversaturated. That means that what happens is light comes in and it converts light to electrons, and electrons give you the image finally. Okay, so they're converted to the image. And sometimes if you overexpose an image, and that's what we see as an overexposed image, they spill over into the next one. Okay, and that's what we call bloom. And you think, well, why do we have bloom? Why not just get rid of them? Well, that is a good point. There are, in fact, it's very possible, and that's what you have in your usual camera. You have anti-blooming. You may not know this, but you have anti-blooming in your camera. And what it basically does is that's a metal grid that sits on the CCD sensor and actually takes and conducts the electrons away, and then you don't have this blooming. But there's a big disadvantage here, a big disadvantage. First of all, your sensor is not linear anymore. If it's not linear, it means that all the astronomers that work in our with our very, very professional sensitive equipment cannot do any exposures, because there will always be stars that are overexposed. Okay, so it means that the detector is not linear anymore, so they can't do proper measurements with it. And second of all, the sensitivity goes down drastically. Because the metal grid is blocking part of the sensor, the sensitivity goes on. So what we do is we say we want a very sensitive sensor, we cool it down a lot, and we don't mind, we'll get rid of this. And I'm going to get rid of these lines now live with you to see that it's not a problem. And what's also interesting now is, let's just have a look at the telescopes. Yeah, I think that's a great idea. Let's just let me show you what the telescopes actually look like, because that's really important. I mean, to understand why we're using what. Okay, so this is T30 that you're looking at right now. This is T30, and you can see this is a 0.5 meter aperture. Okay, so this is a 0.5 meter aperture, and what's important is the picture that you see down here. That is the key thing. I'm just going to get the arrow out of the way. 1 second. There we go. This shows you how large, this is on the Orion Nebula, how large the sensor actually is, what you're looking at. Not how large the sensor is, but what your field of view actually is on the sensor. So you're seeing quite a bit of the Orion Nebula. So it has a 0.5 meter aperture, and you're seeing this much. So what does it look like on the T27? Now, T27 is a marvelous piece of engineering. It's the biggest telescope we have. It's 0.7 meters. And it's also interesting because it's not an equatorial mount. It's what we call an alt-az mount. So that gives some complications, which I will not go into, but it gives very, very beautiful tracking. It's very, very accurate. And as I scroll down, can you see the field now? You can see that the field is a lot smaller. So now comes the interesting question. You could say, well, why are we seeing these lines on T30 and not on T27? Well, the answer is quite simple, because even though T27 has an aperture of 0.7, which is a lot larger than 0.5, it will take about twice the amount of light, because it's the square of the aperture. Okay, 0.7 squared or 7 squared is 49, 0.5 squared is 25, 49 by 25 is roughly 2. So it takes about double the amount of light. However, the focal the focal length of T30, which I'm showing here, is a lot shorter, which means the field of view is much larger. And basically, what matters in the end is what the resolution per pixel is. Okay, sorry for all the technical jargon now, but it turns out that the resolution of the larger telescope, which is the one I'm showing here, is much, much better, and that's why it is actually collecting less light per pixel. It has better resolution, but it's collecting less light, and that's the reason why we're seeing these long streaks on T30 and not on T27. So important to understand this when you do images, because there's nothing wrong. There's really nothing wrong. On the contrary, everything's fine. So here we go. Now we're going to have some fun. Let's get rid of this first of all. So why I like CC Stack a lot is they have something that called process, and you go to, I'm going to get rid of these lines, and it's called data reject procedures. Oops, and let me just get, the window is unfortunately on the wrong, let me just get this over again so I can show you this. Here we go. Now you should be able to see it. It's called interpolate data, the data reject. It's got all kinds of different from menu options. What we're going to choose here is reject blooms. That's what I've just been talking about, these blooms. I don't like them. Get rid of them. So apply to all, and here we go. So let's see if this worked. And you can see they're gone, but there's something left there. They're sort of, it's marking that they're gone. What we now have to do is we have to interpolate. We have to tell them, well, I don't want to leave something black there. What I want you to do now is I want you to just fill in that, but fill it in a clever way. So let's just see, where was it? Data reject screen. No, what happened to it? 1 second, let me just close it and open it. Sometimes not so easy to... Ah, there we are. Here we are. It's back. Okay, so I'm going to say interpolate rejected pixels. That's it. Apply to all. So and say, okay, we are going to bright and there we go. Very, very nice. And you can see it's a lot better. Drastic improvement. But they are not aligned yet. And you can see now it's very, very interesting. This software is so powerful that it can align the images. So I'm going to align these images and then we're going to compare them. Wrong button? Sorry, did I do something wrong? Wait a sec. Did I? Not sure. Brian, were you complaining about me? No, I don't know. Did I do something wrong? I'm not sure. Cannot hear you, screen frozen. Wait, can you hear me? 1 second. Screen frozen. Let me see what's going on. Okay. Okay. Lost me. The screen is buffering. Okay, let me see what's going on here. 1 second. Okay, I just need to check what's going on. YouTube. Let's see what's going on. Events. Okay. 1 second. I seem to have lost everyone. That's not good. That's funny. 1 second. My screen is buffering. That is weird. Okay, I seem to be back now. 1 second. I seem to be back. Image and voice gone. 1 second. Image and voice gone. Can you hear me now? Image and voice gone. I'm not sure if you can hear me now. That's strange. What is going on here? That's a bit disturbing, isn't it? No, okay. Sorry. That's weird, isn't it? Let me see what I can do here. Let me see. That is weird. That is weird. Still no. Okay. Still trying. Still trying. Can you hear me now? Oh my goodness. I so apologize. I have no idea what I don't know what the what the technical issue is. I apologize. I'm glad I'm back. I'm sorry about this. I really apologize. And I have no idea what it was. Today I have a bit of technical issues, so thank you for being patient. That's not sometimes not so easy. You hear me? That's great. So give me a chance. That's great. Thanks everyone. Okay, let's do this second image now. Let me just jump back into Wirecast and see this. And you should be able, let me get your comments back and everything so I can see everything again. Very good. Okay, we are back again. Thank goodness for that. Okay, so just keep on talking if that you hear me and so on, and then I will know. I will try and improve this next time. So you should be able to see the screen again. So what we did here is we just got rid of the bloom, okay? So we just got rid of the bloom, and let's make some color images now. So the next thing we have to do is exactly the same. We are going to, let's see, blink through them, interpolate, apply to all. We've done this. So let's see, stack, register. We have to register. This means align them all. Thank you for the teaching. That's great. Yes, we'll show you get rid of the blooms. Yeah, we did. And we got, so what I did is you lost me again. Wow. I wonder why. Oh. Lost again? Really? Oh my goodness. Is that... That is weird. Oh, I can hear you. Good. Okay, sorry. Let's try. Okay, now I'm going to align them all. I don't know if it's the software. Good. You did not lose me. Thank goodness. This is really frustrating for you and for me. Okay, I'm going to hurry up now. We've aligned them. We've got rid of the blooms. Yeah, thank you, everyone. I've got rid of the blooms, which is great. I've just aligned them. The alignment is going to be good. Now, this is going to take a minute or so because this is very, very heavy maths it's going to do from 9 images that look completely different, by the way. Okay, so here we go. We've aligned all the images, so I'm going to blink through them quickly. There you go. Look at that. We have aligned all the... You can hear me. I'm so glad. It's so frustrating. It really is frustrating. So there you go. We've aligned all the images, and you can see they're all fine, right? So they're perfectly aligned, they're turned around. You can see one is a bit wider than the other, but now we can go and do color images, and that's nice. So I'm going to say pause, and here we go. Color, create color, and here it already recognizes them straight away, and I'm going to say create color, and there we go. And it again says, what is your background? So I'm going to give it your background there. Do the same, apply, and there we go. We see a beautiful image of the Lagoon Nebula. Isn't it fabulous? So I'm going to just magnify this a little bit in for you. Let me just take the magnification window over so you can see what I'm doing here. I'm just going to say magnify the image. There we go. So it's properly on the screen. And you can see that's not bad. That's actually quite remarkable. This is one single, so it's 20 minutes in total. The lumens red, green, and blue. And we get incredible detail, okay? Beautiful detail. And now we're going to do the same with the other telescope. I think this was T27. Yeah, this was T27. And now we're going to do exactly the same for T30. So let's just do it. I'm going to say again, color, create. And now you see it doesn't know of T30 that which one is red. I just have to look for the red one here. Let me just find out. Sometimes not easy. Reload. No sound. Image frozen again. Is it really? No sound. Oh my goodness. Reload. Oh no, really? This must be some error. Oh gosh, you have no sound. Okay, here, thank you. Okay, I'm glad. I apologize if this. Okay, good. Well, today is not. It's April Fool's Day. Let me see. Is this the red one? It's April Fool's Day. No, that is not the red one. Let me just see which one it is. Here's the red. Here we got it. You got okay. Okay, so I'm going to say create now. Here we go. And again, it looks like the image is not very nice. So I'm just going to select the background and say apply only to this. That's fine. And here we go. And that's the second image. And again, we can correct the colors a little bit if we want to. Give it a little bit more red and so on. But that's basically it. And now that's really nice because we can now run through both images. And here you go. That's the one. That's T27. And that's T30. And the colors look a bit more bright on T27. No surprise, because the camera is a 9 megapixel camera, and also it's got a bit more aperture. So for the short time, the result on T27 is very, very noticeable already. And that's why it's such a big favorite. It's a bigger telescope than the other one. However, if we take more images and we stack them, we can do just the same with T30. Okay. So anyway, I think the images turned out beautifully. And let's talk a little bit then about the Lagoon Nebula. Okay. Finally. So let me jump back. Just let me get your, so I can see your comments. I'm going to move your comments to my other screen so I can see all that. That's fine. So this is again, this is beautiful work from Giuseppe. And what he's done there is he's taken many hours of depth, including narrow bands, and you can see how beautiful the Lagoon Nebula comes out here. What is really remarkable about this image that he's done is you can see there's a little bit more blue all around here. That comes from the oxygen, okay? He's given the bluish color, that's a little bit more oxygen. The center is definitely more hydrogen. And then as you go to the deeper and deeper red, you get a mixture of hydrogen and sulfur. So you can see all the very different compositions of the nebula. And that gives this incredibly detailed structure is only possible with narrowband. Okay. So, and in the center, right in the center of the Lagoon Nebula, again, is a very, very young so-called O star. It's a huge star that is giving a lot of ultraviolet light to illuminate yet another star factory. By the way, the Lagoon Nebula is also approximately 5,000 light years away. All these big nebula that you see are typically approximately that distance. Okay, so the Running Chicken Nebula we did earlier was about 6,000, and there are errors here about 1,000 or 2,000 light years easily. Okay, so anyway, I hope you enjoyed this, and I really am sorry for these strange interruptions. I really don't understand where they came from, because my signal was good, but I was a bit unfortunate that my laptop wouldn't let me in just a minute before I started the show. Well, that's part of a live show, and I hope you forgive me. I'm really multitasking here. I do hope you enjoyed it, and I hope you saw that. What I'm going to do, don't forget, all these images are going to be available on the episode 8, probably in a few hours. Just give me a few hours. I need some breakfast and so on. And then I will upload all these images for you, and you can freely download them. Just go back to episode 8. By the way, go back to episode 7 too, for those of you who joined later, and you will be able to download all the images from last time, the active galactic nucleus there. That was one of these black holes with these incredible sort of laser-like plasma streaming out of the center. That was NGC 49. What was it? 4995. I think that was the one. That was the one we did last week. And do come back next week, same time. And then especially in 2 weeks' time, we're going to have Saturn. Saturn. Don't forget, in 2 weeks' time, you're going to have Saturn. It's really, really beautiful. Big show. And then I'm off to Australia. So you're going to see me live also in Sighting Spring. And I will announce those as I arrive and so on. So I think then I will be in Australia from the 19th of April to about the 4th of May. I'll be driving around in a camper van, and I'll giving some live shows from some dark places, and I'll also be visiting Pete at Sighting Spring and giving some live shows from there. So really exciting things coming up. So my astro friends, I hope you enjoyed this session, and thank you again for your patience, and have a wonderful day. Okay, thank you. So let's see now. I just have to switch this off. That's it. Okay.